สวัสดีครับขอต้อนรับท่านผู้ชมทุกท่านนะครับเข้าสู่กิจกรรม FI เกษตรศาสตร์นะครับเวบินาร์นะครับในครั้งนี้นะครับเรามาในหัวข้อนะครับการถ่ายทอดเทคโนโลยีข้ามพรมแดนเพื่อเพิ่มขีดความสามารถในการแข่งขันของอุตสาหกรรมไทยหรือ Cross Border Technology Transfer ซึ่งครั้งนี้เป็นครั้งที่3นะครับและในวันนี้นะครับเราจะพูดถึงเรื่องเทคโนโลยีการแช่เยือกแข็งแบบไครโอเจนิกในการสกัดและการยืดอายุการเก็บรักษาของส่วนผสมอาหารฟังก์ชันหรือ Cryogenic Nitrogen Technology for Enhancing Extraction and Preservation of Bioactive Ingredients in Food นะครับซึ่งกิจกรรมนี้นะครับได้รับการสนับสนุนจากเมืองนวัตกรรมอาหารส่วนขยายณมหาวิทยาลัยเกษตรศาสตร์และหน่วยบริหารและจัดการทุนด้านการเพิ่มความสามารถในการแข่งขันของประเทศหรือบปข.นะครับซึ่งวันนี้นะครับเราจะมีผู้ด้วยกัน2หัวข้อนะครับซึ่งหัวข้อแรกก็คือ Pressurized Cryogenic Nitrogen Technology a novel food processing for future bioactive ingredients preservation นะครับโดยวิทยากรจากต่างประเทศนะครับ Professor Stefan de Sobri นะครับจาก National Engineer School of Agronomy and Food Industry จากมหาวิทยาลัยโลเคนนะครับประเทศฝรั่งเศสนะครับแล้วก็อีกหัวข้อหนึ่งนะครับก็คือหัวข้อ Opportunity of Pressurized Cryogenic Nitrogen Technology for Food SMEs นะครับ Pilot Scale Application โดยผู้เชี่ยวชาญจาก Generalist Avinia Innovation Base ฝรั่งเศส โดยมิสเตอร์กิโยมกิเลตนะครับและนอกจากนี้นะครับเรายังได้รับเกียรตินะครับจากผู้ดำเนินรายการภาคภาษาอังกฤษนะครับของกิจกรรมในครั้งนี้นะครับนั่นก็คือผู้ช่วยศาสตราจารย์ดร.กิติพงษ์รัตนาพรนะครับท่านเป็นอาจารย์ประจำภาควิชาเทคโนโลยีชีวภาพคณะอุตสาหกรรมเกษตรมหาวิทยาลัยเกษตรศาสตร์ครับและเพื่อไม่เป็นการเสียเวลานะครับเดี๋ยวผมขอมอบช่วงต่อไปนี้ให้กับผู้ช่วยศาสตราจารย์ดร.กิติพงษ์รัตนาพรครับ
สวัสดีท่านผู้ฟังทุกท่านนะครับผมก็วันนี้เป็นเกียรติอีกครั้งหนึ่งนะครับสำหรับมาเป็นผู้ดำเนินรายการภาคภาษาอังกฤษของการบรรยายพิเศษนะครับของโครงการเมืองนวัตกรรมอาหารส่วนขยายณมหาวิทยาลัยเกษตรศาสตร์นะครับผมผ่านโครงการcross border technology transfer นะครับในวันนี้เป็นตอนที่3นะครับเกี่ยวกับในเรื่องของ Cryogenic Nitrogen Technology for enhancing extraction and preservation นะครับเราได้เชิญผู้เชี่ยวชาญจากต่างประเทศนะครับก่อนอื่นเดี๋ยวผมขออนุญาตแนะนำผู้เชี่ยวชาญจากต่างประเทศให้ทุกท่านได้รู้จักนะครับGood afternoon, everyone. Today we have Professor Stefan Desobri from the National Engineering School of Agronomy and Food Industry, Lausanne University, France. Before he gives a talk, I would like to introduce him briefly. So, Professor Stefan is now a full professor at the University of Lausanne at the National School of Agronomical and Food Science in Nancy. He used to be a head of the International Master in Food and Packaging Preservation and also the coordinator for the French Embassy in Algeria of bilateral network for Franco-Algerian Engineering School to support the reform the 29 Algerian higher schools from 2007 until 2020. He also an expert for the evaluation of European projects since 2011. He supervised many PhD students and master students at Lausanne University, and he published his research work about 170 international publications. He launched 6 patents and 11 book chapters and more than 100 international communications. And right now he's an expert in preservation of food ingredients, especially for bioactive compounds and also microorganisms and also algal cells. And today we are pleased to have him to talk about the cryogenic nitrogen technology for enhancing extraction and preservation of bioactive ingredients in food. If we are ready, please join me welcoming Professor Stefan for his talk today. Good afternoon, Stefan.
Good afternoon. Thank you very much for this introduction. And thank you for inviting me. It's a pleasure for me to be here. Maybe I can share my screen?
Yes, please. Thank you.
Can you see the slides?
Yes, very clear.
Okay. Well, thank you very much. So maybe I will start the presentation. I will just reduce this. Okay, so thank you very much to all of you to participate to this meeting. I will give you a short presentation about the cryogenic freezing and particularly a new technology based on pressurized cryogenic nitrogen technology to improve preservation of bioactive ingredients. And I will give you some details about this technology today. So first of all, some words about the freezing process. The freezing process is largely used in the world to preserve foods, to give them long shelf life, and to ensure food safety. As you know, you can find water in 3 different states. On the right, you have the gaseous state where water molecules are free one from the other with no connection. They are in the air. In the middle, you have the liquid water. In this liquid phase, you have interaction, small interaction between water molecules, and this gives you a fluid that you can move, you can displace easily the water molecules. And then on the left, you have the structure of ice, in which you can see some holes. These holes are linked to the organization of the water molecules, one from the other, with a really rigid structure and with no movement possible. If you study more precisely the state diagram of the water, you can see the three states of water with the vapor state for low pressure and high temperature, the liquid state, and the solid state for the lowest temperature and commonly below 0 degree. You see also on this slide the pressure axis, and this axis was used in the new technology that I will present to you to try to increase the pressure of the water in the food and to see what happened to better preserve the active biomolecules. Depending of the pressure on which you are working, you can have different states of the ice, and you can see here a phase diagram for very high pressure, where you can see different type of ice. The one we know, the common ice, is the type 1 that you have at the bottom of the figure, and then you have the second structure of the ice, and then third one, fourth one, and so on. And so you have, depending of the pressure, different structure of the ice, and the molecules organized differently one from the other, depending of the pressure that you apply when you try to freeze the product. At the bottom of the diagram, you have a very small rectangle where you can see the states, the zone in which we can work to preserve easily with low-cost processes the food. If we study this small region, you can see that even in this very small region of pressure, so from 0.1 to 10 bars, you can have different types of ice, and each ice will give a specific possible preservation of the product. The interest of this different structure is also that you can have different sensory feeling when you eat the product. For example, for ice cream, you can have different type of ice cream with more smooth or rigid structure of the ice. If we go back to the water structure in the liquid state, we have, even in liquid state, an organization of the water molecules, one from the other, to build what we call clusters. Those clusters are zones where liquid molecules organize one from the other, and so they have hydrogen bond linked between those molecules. And you can see here some small part in which the liquid state is no more really free, but you have interaction between the water molecules, and so you have the increase of the viscosity of the water due to these links, and slowly, with decreasing temperature, the size of these clusters will increase, involving the free water molecules which are around this cluster to build bigger and bigger structure. So at high temperature, when we are close to 100 degrees Celsius, you have just free water molecules. And then when you decrease slowly the temperature from 100 degrees Celsius down to 0 degrees Celsius, the cluster, the size of the cluster will increase slowly, and then will organize to be ready for ice structuration. In this table, you have the data in which you can see that at 60 degrees, for example, the number of water molecules involved in a cluster is 28, and we have 33% of the water which is completely free at 60 degrees. If I decrease the temperature from 60 to 20 degrees, you can see that the number of water molecules involved in the cluster increase up to 57, and there is at that time just 29% of the water which is still free. And when you decrease down to 0 degree, the number of water molecules increase up to 91, and just 24% of the water is still free. And then when you go down to in negative temperature, you have 100% of the water molecule which are linked together to build the ice structure. At the other extreme, you have at 100 degrees only monomers. Oh, sorry. You have above 100 degrees just monomers, and the water movement is so high that no cluster is possible to build, and the water molecules are released in the air with a very fast evaporation. So here I can show you just few structure of ice. The common ice is on the left, in which you have here 6 molecules of water linked together, and you have a kind of holes in all these parts, in which you have a large void, which explains the reason why when you freeze water, the volume is expanded, and you have an increase of the volume of 10% due to the voids that are created thanks to the link, the strong link between water molecules. If you change the pressure and temperature, you can reach other structures which are completely different. For example, this one, you have just 5 molecules of water to build the crystals. And here you have previously 6 molecules. And here, for example, the ice 4, you have a very strange structure with a very difficult organization to explain. So depending on the pressure and the temperature, you can reach several structures and different structure of ice in the food. So the idea is to discuss about the technology that was developed between the university and the Geniolis company. And so we work on freezing for several years, and we generally use, as you, I'm sure, the classical freezing. You put food in your freezer, and then you wait for 20 hours that the food is completely frozen. So this is the simplest way to freeze food. And the idea of this freezing is just to stop microbiological spoilage due to decrease of water activity. I will give you some data about that in the next slides. We will stop also the division process of the cells. So it will stop the multiplication and the growth of the microbial population. And also, of course, at freezing temperature, we are below 0 degrees Celsius. And so in that case, the growth temperature is not possible for most of the microorganisms present in food. So you have 2 main activities during freezing process: temperature and water activity. Another interest of this freezing process is to reduce the chemical reaction speed. Of course, we will stop the microbial spoilage, but by chance, we also reduce the kinetic of the chemical reaction. And so in that case, we can preserve antioxidant, for example, for longer time due to slow reaction of oxidation in the frozen food. So the idea of this freezing process is mainly to increase food shelf life. You have here a picture that was built by Professor Labouza 30 years ago or 40 years ago. And on this slide, you can see the main alteration of food that you can see during food preservation. For example, you have on the blue line, the first blue line, the lipid oxidation. So you see that the kinetic of lipid oxidation first decrease with increasing the water activity of the food, and then increase with the water activity and decrease finally. You have other alteration process as non-enzymatic browning with an increasing after 0.2, 0.3 water activity, and then increasing to a maximum at 0.7, and then a decrease with increasing water activity up to 1. So those two reactions are the most complex. The other one are much more easy to understand with a simple increasing of enzymatic degradation with increasing water activity, an increasing speed of mold multiplication and growing with increasing water activity up to 0.7. Same for yeast at 0.75, and same for bacteria up to 0.8. So most of the food that we like to eat have a very high water activity, and generally between 0.9 and 1. So as you see on this picture, if you stay in water activity between 0.9 and 1, you have a very large alteration of the food because all reactions are able to develop in this area of water activity. When you freeze the foods, in fact, you will cap the free water, the free molecule of water which are in food, to build ice crystals. As you capped the free water molecules, you will decrease the apparent water activity of the food because the water is no more available for all the reactions that are presented on this slide. So when you freeze a product, you will have, for example, the blue line that I show you at 0.95 will decrease down to 0.3 when all the product is frozen, because all the free water that can be used for food alteration are capped in crystals, and there is no more mobility and no more reaction possible. So in that case, the apparent water activity of the food decreased down to 0.3. And as you can see on the picture, there is no more possibility of bacteria growing, yeast growing, mold growing, enzymatic degradation, non-enzymatic browning. The only activities that alteration that can occur is lipid oxidation. That is the most difficult reaction to anneal by freezing. So the idea of this freezing is just so to stop the evolution, the change in food during long time of storage. I must say, nevertheless, that even in frozen state, the shelf life of the food is not eternal, is not extended as the infinite. You have to eat the food within 3 to 6 months after starting the freezing, because even in frozen state, you have oxidation and slow degradation of the structure of the food. So it's not possible to keep it for 2 or 3 years, even if it's not dangerous to eat product stored for a very long time. Just the texture and the sensory quality of the food will be degraded. So the question now is to choose the best way to freeze the food. We have the classical one that I told you previously, the slow freezing, which people use at home to preserve some food that are close to the shelf life and they want to extend it for a few weeks. And so we put it in the freezer and then we wait for 6 to 24 hours to have a complete freezing of the food. At industrial scale, it's better to have much more efficient process for freezing, first to save time, but also to improve the quality of the preserved food. So it's what I note here, the fast freezing or cryogenic freezing, in which you can freeze a product in 1 to 20 minutes. You can see here the liquid nitrogen from the bottle. So it's liquid nitrogen is just as water. The only difference and main difference is that the temperature is 196 degrees below zero. And so you have industrial machine already available on the market in which we use this nitrogen, this liquid nitrogen to freeze very fast the food that you put in the system. If we compare the results of the two freezing process, the slow freezing process and the fast freezing process, the difference are just enormous. On the left, on the picture, you can see a cell in the food. And so we start the freezing of the cell. And during freezing, you have two effects of the freezing process. The first one is to have formation of ice crystals outside the cells first in the food with the free water that I discussed previously. So this free water goes together to form the ice crystals. And as the water quantity outside the cell decrease, you have a flux of water from the internal side of the cells to the external side of the cells. And so the cells will see its size decrease slowly with the freezing process because all the water that is in the cells goes out the cells. So if we do a very slow freezing on the top of the slide, slowly the water will go out the cells and you see that the cells size will decrease and decrease, and finally the cell will be very alterated due to the flux of water outside the cell. If you do a fast freezing, in that case, the water has no time to go outside the cells, and so the crystals will form also inside the cells and will preserve a large amount of water inside the cells and will largely decrease the damage that occur to the cells during the process. So this is the first point. Another point that you can see when you freeze slowly a product is that on the bottom of this figure, you will see large crystals formed in the food due to the large time that molecules have to organize themselves together. And so you have an increase of the size of the crystal. And so the big crystals which just broke the cells due to very strong mechanical effects on the cells. And so after a slow freezing, you have generally a large amount of death of cells in the food. And so the structure of the food is largely destroyed. And when you thaw the product, you have a large amount of liquid water going outside the food product due to the cells that have been destroyed during the freezing process. On the top of this slide, you see that when you have a quick freezing, you will produce a large amount of very small crystals instead of a low amount of big crystals. And so in that case, you have really little damage to the cells. And so you have a larger preservation of the product, and you have not such a large amount of liquid that go outside the product after thawing. So with those two data, you can see that high-speed freezing is largely better than slow freezing. And so industrially, most people try to use cryogenic freezing to freeze foods. So if we compare very quickly the difference between those two processes, you have, for the quick freezing, small size of crystals. But for slow freezing, you get large crystals with a lot of break of the cells involved in the food. If you freeze quickly, you immediately suppress the microbial metabolism. In the slow freezing, the breakdown of metabolic report, and it causes cell damage. The quick freezing is, of course, a brief exposure to adverse condition. For slow freezing, it will take 20 hours, so it's a longer exposure. In quick freezing, you have no adaptation to low temperature. You have no time for the cells to adapt, but for slow freezing, some cells will be able to protect themselves from the gradual decrease of the temperature. And you have, of course, at quick freezing, a thermal shock to microbes, so some of them will die. And for slow freezing, you have no thermal shock, but of course, you will have an increase of the ice crystals and the destruction of the microbes also. And finally, when you thaw the product, you have a low water loss for quick freezing and high water loss for slow freezing. So in most of the parameters, of course, quick freezing shows a better effect on food preservation. So the two technologies that are used at the moment in the industry is a kind of, on the left, the shower technology. So you put a shower of liquid nitrogen on the top of the product, and the liquid nitrogen goes from liquid phase to gas phase and freeze very quickly the product that is in the tunnel. The other technology is an immersion process. So you put the product in the liquid nitrogen, which is faster and generally used for bigger particles of food, and then you get the frozen product. So you have the shower technology and the bath technology, both exist on the market. Let's go now to the processing of pressurized cryogeny. The pressurized cryogeny is something that is not used in all over the world because it was patented by the Genialis technology 10 years ago, and Guillaume Gillet will present the technologies just after my presentation. But I can tell you the interest of this pressurized technology. So you have here the picture of liquid nitrogen that is used for classical cryogeny. When you use classical cryogeny, you have a lot of nitrogen that gets in the food. If you want to use it and replace oxygen by nitrogen, you have to increase the pressure to put much more nitrogen in the product and then replace oxygen within the food and then avoid the oxidation. And this is the first point of interest of the pressurized cryogeny. We will put a larger amount of gaseous nitrogen in the food, and so we will remove all the oxygen that is present in the food. If we just enrich the liquid food before freezing or the solid food before freezing with nitrogen, if we use a classical cryogeny, we get a porous structure of the food. As you can see here on this example, it's just a stone with a lot of holes due to release of nitrogen during the process. So the idea of this pressurized cryogeny is to use pressure to the end of the process. So during the whole process, we stay under pressure between 0 and 100 bars. And so using pressurized cryogeny, you keep the structure of the food without any holes or porous structure. So the food can stay very compact with no alteration of its structure. So you can, with this technology, replace oxygen by nitrogen. So you stop oxidation, and I show you previously that oxidation is the most problematic aspect of the storage of frozen foods. And you have also an intact structure, a dense structure of the food. Moreover, as you maybe know, when you use classical cryogeny to preserve cells, you can add cryoprotectors as glycerol, ethylene glycol, dimethylsulfine, and so on, to avoid the destruction of the cells to sell the yields or bacteria for the end user. So with this technology, we use the critical point of the pressurized cryogenic domain. You see that when you reach the critical point, you change the structure of the water, and you have a completely different preservation of the food. So the idea is to stay below this critical point and to work in pressure that are easily reached with low-cost equipment, from 1 atmosphere, from 1 bar to 25 bars. So in this area, we see with the experiment we did that we have the protective effect of the nitrogen against oxidation, but also a very nice preservation of the food structure. And so the technology was protected, was patented in this area of activity. So the first equipment that was built was like this one. It was called the CryoSurvive technology, in which the liquid nitrogen is put here in a chamber down to the machine, and then we put the food inside and we increase pressure from 1 to, in this experiment, to 100 bars to check the effect of all the pressure on the structure and the oxidation of the product. Guillaume Gillet will give you much more information about the equipment that was developed from this first one to the present one. So when the product is frozen, we study the stability of the product, and we show that oxidation was no more possible because you have a very small release of nitrogen during all the preservation time, because a lot of nitrogen is dissolved in the food, and so it avoids any entrance of oxygen in the food, and so you preserve all sensible molecules that are present in the food. And we go further, and we decided to see nitrogen if it could be of interest, and so to freeze dry the product entrance of oxygen in the food, and so you preserve all sensible molecules that are of interest. And so we freeze dry the aroma preservation oxygen in the food, and so you preserve. So after cryogeny work, you have here some examples. So the aroma preservation flowers. So after cryogeny extracted from rose, from wisteria, from purple lilac, for example. So after cryogeny extracted from rose, extract are very sensible to oxidation. If you just freeze them, their shelf life is a few days at the maximum, because oxygen very quickly oxidizes the aroma molecules. So with this pressurized technology, we entrap a lot of nitrogen within the beads, the frozen beads that you can see here. And so oxygen is not able to get in the beads and to oxidize the molecule. You have here a comparison of two composition of purple lilac with a classical cryogeny, and which is called reference, and the pressurized cryogeny in blue. So what you see is that the peaks of the aromas are generally higher with the pressurized cryogeny, and you have molecules that are still existing in the pressurized cryogeny that has completely disappeared after classical cryogeny. So with this comparison, you can see that pressurized cryogeny will preserve much more higher number of aromas molecules in the flower aromas. Another example with the truffle. Truffle is very largely used for foods with a very good taste. And you see here also that you have much more peaks with the blue technology, so pressurized technology, compared to the reference technology. And when we test the product, we can feel a difference in the test due to the better preservation, and the initial truffle is close to the frozen truffle. To compare the diagram, the peaks diagram of aromas molecule between the two processes, you see that at 6 bars, so in pressurized technology, you can see on the black figures that you have much more peaks on the right sides of the figure than on the blue picture, where most of the peaks disappeared. And if we superpose the two pictures, you can see that you have larger amount of peaks with a black color corresponding to pressurized technology compared to the classical cryogeny. Last example that I can show you is a coffee preservation with increasing the pressure. So you have, in most cases, a larger peak for the pressurized cryogeny, so the blue or the black line, which are two pressure used for the technology, and compared to the reference, which is in red. So in most cases, you have a better preservation of aromas for all the products that we tested with this technology. Just a comparison here with very sensible aromas that are still existing. So you can see peaks that are still existing in black and at completely different, disappeared in red, as previously described. So the second interest of the technology is that when you plan to do freeze drying, you have a largely faster process of freeze drying due to the presence of nitrogen in the food. When you freeze dry the food, you have release of nitrogen, which increases the speed of water evaporation, and the time is decreased by 2 between the classical freeze drying and the pressurized technology freeze drying. Here you see, for example, at 6 bar, the duration of the freeze drying is 16.5 hours compared to the 33 hours of the reference classical freeze drying. So this is of importance for industry because the time required for freeze drying is very costly for the company. Other effect that you can have on freeze-dried product is the decrease of the density of the powder. For example, here you have the same mass of powder in the 3 boxes. The reference, you have a very dense powder, very difficult to hydrate. But when you use pressurized technology, you have a lighter density. And so you have a much more rapid radiation of the product. You can see here that with the reference, you have large particles and very dense particles of powder, and increasing pressure will give you the possibility to decrease the density and to have very small pieces of powder, and so it will increase the radiation time, which is largely interesting for industrial application. And the last point that I want to show you is also the preservation of microorganisms of interest. For example, here the Saccharomyces cerevisiae. So you see that we compare the reference freezing, so classical cryogenic freezing, and 25 bars pressurized technology. You see that you have cracks on the surface of the mold on the left, and you have no cracks on the right. So the technology, the pressurized technology, allows a largely better preservation of bacteria or yields or molds of interest. Just to finish the presentation, the way on which we are working, you know probably this, I will go back, you know probably this type of diagram. It's a state diagrams of food using the concept of glass transition. And this concept of glass transition can explain the stability of the product at various content of water. And the idea with this cryogenic technology under pressure is to go further and to develop a new axis on this diagram, the pressure axis, and to see the change that can occur in the crystallization, collapse, and caking, and so on under pressure. And so this technology will open a new field of research to study that condition that nobody studied before using high pressure and different water content, and to see what happened and to modify these classical graphics that all the students study at university. And so with the process that we use, we increase the pressure, and then we decrease the temperature, and then we reduce the pressure, and we see the change that occur in this classical diagram. So this is a research part of what we are doing at the moment to better understand the technology and to develop new application from this technology. And so at the moment we are studying a lot of systems, and we are trying to find partners to study all the systems in the biology field, but also in food fields. And so I hope that we can collaborate in the future on several of these systems with this new cryogenic technology. Thank you very much for your attention.
Thank you very much, Stefan, for your wonderful talk today. It's really interesting about the technology that you share to work with the bioactive compounds in the agricultural products and other applications. We got a questions about the technology. So for this technology, do you think if the industry would like to use this technology to apply for their food processing, do you think what is the constraint of the raw materials that they need to concern before applying this technology to their products?
In fact, at the moment, we didn't see a large limit of the technology compared to the classical technology. The only point is, of course, that we have to develop a type of feed of the machine depending of the size of the food, if it's liquid, if it's solid, it depends. So the feed system will vary depending on the food, but in fact the process will not change from one food to another. And we saw that in fact the preservation is largely better in most cases, even for big solid food. It's at the moment it's difficult due to the feeding, but for small solid foods it's fine. For example, fruits, vegetables or something like that, it's fine. If you have big piece of foods, it's much more difficult to have pressure and freezing at the same time for big foods, but it's something that we are working on.
So and another question is right now I believe that you implement this technology in the industrial scales there in France. Can you give us examples of the products that you apply this technology for?
I can do it, but I think that Guillaume will present it in his presentation.
Oh, okay.
He will show you a lot
in
of
the next part.
So he will answer the question.
Okay. All right. Thank you very much. And if we have any more question, we would post it for you, and we would answer the question to the audience online. Okay. And thank you very much for sharing this novel technology with us today. And I hope you have a great day today. And we will move to the next presenter. Thank you, Stefan. All right. We have the second talk from the company. So today we would have Dr. Guillaume Gillet from Gialis company. So hello, Guillaume.
Good afternoon.
Good afternoon. So I'll give a brief introduction of you to the audience, and then I invite you to give a talk, okay? Okay. For the second talk today, we have Dr. Guillaume Gillet. He's Research and Innovation Director of Gialis company in France. He finished his doctoral of engineering from INPL SAIA Laboratory of Food Science and Engineering from Nancy, France. So, and he also food industrial engineer and specialization in food packaging, and he has a degree on that. before he becomes a director of research and innovation at Genalis company, he was a researcher and worked as a manager of the research and R&D projects, supporting the for industrial development to carry out the test of the products of the clients. So today we have Guillaume Gillet, and he would share his experiences and the industrial application of the cryogenic nitrogen technology for food preservation, especially to demonstrate for Thai food SME to see if any opportunities to operate this technology in Thailand. If you are ready, please join me. Welcome Guillaume for his talk today. Please, Guillaume.
Yes, thank you for this introduction. So good afternoon again to everyone. I will share my screen. My presentation is a complement to the one that made Stefan before. And I will more talk about the equipments and the application of the technologies that already exist. First, to present the company, Genalis is an engineering company. So we are making new technologies, new developments. But our particularity is that we are starting from laboratory scale. So we are first researchers, but we are also doing developments right to the applications. So we are developing new technologies, we are developing new equipments, and we are developing also new products. And we are making some tries directly on the market to see if our applications and if our technologies are have a reality, economical reality on the market. Our second particularity is that we are not doing this alone, because we are only 8 people in Genalis. We developed a large research partnerships with experts, with universities to make all these developments. Just because it's on the presentation, we won a Ministry of Research competition in 2007, and that's what make about the creation of the company. So today we have a portfolio of 14 patents, all with green tech orientation, and 6 of these patents are dedicated to the pressurized cryogenic process. And our business model is based on licensing processes and selling equipments for laboratories or for industrial processing. Because we are developing technologies, we have a lot of fields of research and application. And so we are working on food products, on nutrition, on body and skincare products, and also on pharmacy. So let's talk about the process. I will describe more the principles of the equipments because Stefan made a very good presentation of the concepts and of the science that is beyond the process. So we are in our equipments, we are making bets of products, and we are making it in 2 different ways. In batch processes, that's for laboratory or small equipments, but we are also able to make bets in a continuous way. That's what I will talk about just after this slide. So the bets are made by pumping products through a shower to make droplets. And we have two steps in our process. First is a gas dissolution, which is operated by partial pressure equilibrium during the fall of the droplets from the shower to the nitrogen bath. And the second step is the changing of state of water. So product is changing from a liquid form to a solid form. And that's what trap the gas into the product. And that's what give the properties of the product during the conservation and during the utilization. So to make this, we have a tank which is under pressure, and we have a nitrogen bath. In the continuous form of the process, you will have something which is almost the same, but the most difficult part, technically difficult, which is difficult, sorry, is the rotary valve, which is here, because we have to extract products from a tank which contains liquid nitrogen, which is under pressure, and we don't want to extract liquid nitrogen, and we want to extract products slowly without some how can I say that, with the gas which will
with depressurization.
Yes, we don't want a depressurization of products in the room where we are extracting them. Because if we do that, beds will fly anywhere in the room. To say that. So the great difficulty is here, and we succeeded in doing this. So you have a great big bath of liquid nitrogen with a conveyor inside. The liquid nitrogen is injected continuously to have a constant level in the bath, and we are doing droplets right up to the bath, and we are extracting them continuously. The very first equipment that we had was this one, the one that you can see on this picture. So you have the black small tank was the one containing liquid nitrogen, and through the small window here, you can see droplets that are formed, falling into the bath. To make the first scale up of our technology, we made a very big equipment, which is the ones that you can see on this picture, with 4 tanks. In fact, a small one that you can see on the picture, but the first one of 100 liters in one, you have a gas dissolution. The big one that it seems squared because of the thermal isolation was the one containing the liquid bath, where we are making the solid beds, and one at the bottom in which we were separating liquid nitrogen from the beds. This equipment was able to make 70 kilograms of product each 14 minutes. That was progress, but was not really industrial. But that's why we developed something very different next. And the first equipment that we installed in an industrial a company was this one in an industrial factory. was this one. So we changed our approach and made that you can see here is an horizontal tank containing the conveyor, containing the shower, containing everything that we need for our process, and which is, I guess, very compact compared to his ability to make produce at up to 520 kilogram per hour. What you can also see on this picture is on the left, the tanks that contains products. So in this case, it's sauces. And on the bottom, beyond our equipment, that what you see is a cleaning in place process. So it's not directly related to our process. We also developed a semi-automatic pilot equipment, which is this one that we call the Lab 50. Lab 50 because you can do up to 50 kilograms per day with it. And you can also make from 300 grams to 3 kilo per batch that you are making with this equipment. So it was designed to allow on the one hand laboratory scale trials, so for research or for new developments, but also to make small industrial tests, because 50 kilograms per day make you able, for example, to make products for a restaurant or for a small test on the market. And at the end, the last equipment that I will present is the one that Stefan also presented. It's one that allow us to make tries up to 100 bars. That's the only ones that can reach this pressure. The other are developed only to make products only from 2 bars, I would say, to 10 bars. It's because the applications and essentially the food applications are in these pressures. We don't need to have a big pressure for all applications. I will illustrate it. I have a small video that it's just to show you some illustration of our equipment when they are using. So that's a pilot scale equipment. In this example, we're making bits of spirulina. So you can see the Lab 50 equipment, sorry. And next, you will see that's our demonstrator equipment, and that's the industrial scale, which can make up to 520 kilograms per hour. You can see here it's a tactical screen to control it. And here you can see at a small you can see bits that are going from the equipment. Sorry, stop it. So next I will show you some example of applications. So first we developed the technology to make coffee without any machine, any equipment. So by making beds of coffee containing gas dissolved in it, when you are heating these beds in a glass, for example, you will obtain a liquid coffee with the foam at the surface of the liquid. that's a very, you can obtain this effect only with gas dissolved in the product. If you just freeze a coffee, maybe you will have good coffee and good conservation in the time, but you won't have the foam at the surface because this foam is made by the releasing of the gas contained in the beds. And I made a try, it's just for fun, but by making a coffee at 60 bars, you can see that you have something like it's almost foam at the end. You have a very, very small quantity of liquid coffee at the bottom of the glass. Stefan said it also, but we have a very great sensority integrity of products that we are processing with our equipment. For example, fruits or vegetables are very, very sensitive to oxidation, and you can protect them from this alteration by using the pressurized cryogenic process. The main example that we make in our demonstration is orange juice. That you can have a very fresh juice conserved in the freezer when you made it with a pressurized cryogenic process. And the taste is very not the same that you can obtain with other classical preservation, which implies pasteurization. Another effect of the process on the product when you are using them is a phase separation effect. If you have beds of products that you can melt as you wish, if the density of the product are significantly different, so you will have always the same separation with the highest density product, which will be at the bottom of the glass, and the products which have the less density, which will go up in the glass. You can combine effects. So that's example of a cappuccino by melting beds of milk and coffee. You will have the coffee at the bottom and a milk with a foam milk, which a part of foam up to the glass. So I will not detail all the example because it's always the same. I guess you will understand. You can have several uses for products, so you can eat them as a granita, for example, when it is fruits. In this example, it is beds of mint. And chocolate, for example, that you have a frosted chocolate, which you can eat in frozen bits, or you can eat it to have a hot chocolate. And you will have the form that is a very good particularity of our process. Stefan said it, so I will not repeat it again. So you will have a long-term preservation of products which are sensitive to oxidation, like milk or soya milk. Just an illustration of professional applications. In this case, this is the realization of an ice cream which is made by a French chef by using some bits of our product made with our technology and some cream, and just by melting them with a shaker, you will have a perfect ice cream in just less than one minute. To finish my presentation, I will just talk about the preservation of active biomolecules and cells with our technology. First, we'll show you a comparison of survival rates in a liquid culture of Lactobacillus bulgaricus. And this picture shows a comparison between a product freeze in a classical condition in a freezer at 20 degrees below zero, and some different conditions that we can have with our equipment. So we can make, you can create vapor condition controlling pressure, temperature, and density of the nitrogen that is put on our technologies, on our equipments. Vapor condition, it's to explain it, is that nitrogen is present in the tank, mostly in the vapor form. So, and we can also create liquid nitrogen, which will have a different impact of the cell preservation. Before changing the pressure, we will also change the temperature condition and the density condition. All these three parameters are physically related. We can also use supercritical conditions. So it's with a very high pressure and low temperature. Thank you. And you can see that we can control survival rate. If we want to kill some microorganisms that you don't want because they are, for example, pathogens, you can have conditions which will increase preservation, but you can also, if the microorganisms are of some interest, you can also use conditions that will make them able to survive better. And these applications are also possible with a combination of a freeze drying process. So in this example, you can see that increasing the pressure of the cryogenic process, you will increase the survival rate of microorganism. Also, during the freeze drying process, I said lyophilization, it's a freeze dry in this slide. Sorry. The comparison was made with the frozen at 80 degrees below zero because it's the reference when we are trying to preserve microorganisms. And just to conclude, I will show you some other example of cell preservation that we can see in microscopy, extraction from spirulina. And another example of active biomolecules preservation. When you are increasing a pressure, the number after SP on the diagram is the pressure that we use. So F is the reference on the classical freezing. N is nitrogen. We use the nitrogen bath, but without pressure. And after that, we use increasing pressure. And you can see that the more you increase the pressure, the more the active biomolecule is preserved at the end during the time. And that's a very interesting result because we didn't expect it that at the beginning of our study, that the effect of the pressurized cryogenic process implies an effect that will have a long duration in time. I will say that even after some process like the freeze drying process. So that's the last slide of my presentation. And I'm here to answer a question if you have some.
Much for showing us the applications of this technology there in France. And with this application, you see that there are many wonderful products and very beautiful products, especially for drinks, that they could use this technology to develop any kind of beverages with very fresh and full of active compounds. So we got some question from the audience. The first question again, the audience asks about, are there now any these technology, they mean pressurized cryogenic nitrogen technology applied in Thailand yet? I would ask you that for journalists and this equipment that you developed with Stefan, are there any company that selling this technology in Thailand or even in Asia right now?
No, no. We are the only, the equipments are sold by Genialis. So, and today we sold equipment only to French companies, but some of these companies have factories all over the world, but there are no equipment in Thailand yet.
Or any places in Asia?
No, all our equipment are in France right now.
Okay, in France only.
Yeah, France, and we have some implantation that are okay. We plan, sorry, to have some installation in USA now and in Germany.
Okay. And according to the pilot scale for R&D in any research institute or in the university, are there any university or places that have or do their research with this technology with the equipment that you develop right now?
No, the equipment was developed just before the COVID, and so we the only equipment which is in an academic environment is the one that Stefan used. So,
okay, there's only one place in the world right now so far.
No,
okay. All right, the next question is about the storage condition of the products from this technology. The question is like, how could we store the product that we produce from cryogenic nitrogen technology?
So the only constraint you have is the melting point. So if your product have is still solid at 0 degree, for example, if you are processing juice fruit, for example, you can keep it in a classical freezer at 20 degrees below zero. You don't need specific storage conditions. That's not because you are processing the products at 196 degrees below zero that you have to keep it at this temperature in the time. The only thing you will have to check is that your product will not become a liquid again if you are processing the liquid when you are storing it.
Okay. Maybe the last question from the audience. We saw the demonstration of your presentation of the food products. We saw like coffee, fruit juice. Are there any whole fruits that you could apply this technology to freeze them?
Yes, but we made it at this day only at a laboratory scale. So we were processing raspberry, for example, or small fruits like this one. And we are developing right now some evolution of our equipment to process bigger fruits. We also made some developments on seeds, like what can I use as example? Flower seeds or fruit seeds. It works very well, and we made an exposition. It's not a scientific exposition, but in an artistical environment of vegetables that we made grow from seeds that were treated by pressurized cryogenic process. That was a particular experience of Genialis. Yeah.
So last but not least, for the cost of the processing, do you have any information comparing of the cost of the production between this technology and typical freeze drying technology? How about the cost?
It's not very different because the only cost related to our technology is the nitrogen consumption. Electrically, we need a very few energy because all the energy that we use in our process is the energy that we for the liquid nitrogen energy. So it's the main cost of technology, and you will have the same cost using pressurized nitrogen cryogeny or using all other cryogenical technologies.
Okay, thank you very much, Dr. Guillaume, for your presentation today, and we hope that we would have you and your company and also Stefan for the opportunities for the collaboration of this technology to transfer maybe the pilot scale equipment to Thailand, maybe very soon. So thank you very much for sharing us the demonstration of this technology in the lab scale, through the pilot scale, and also in the industrial scale. And we hope that in the near future, we would have a chance to invite you all to demonstrate the real technology in Thailand again soon. And today we finished your talk today by the end of this session. And thank you very much. And we hope you have a great afternoon and have a great day there. Thank you very much.
Thank you very much. Bye.
ไปครับก็จบลงไปแล้วนะครับสำหรับการบรรยายพิเศษนะครับในโครงการ Cross Border Technology Transfer ในวันนี้นะครับผมซึ่งเป็นเทคโนโลยีที่น่าสนใจนะครับถือว่าเป็น Novel Food Processing อันหนึ่งนะครับซึ่งอย่างที่ทุกท่านได้รับทราบจากการบรรยายของผู้เชี่ยวชาญทั้งสองท่านนะครับท่านแรกเป็น Professor ในมหาวิทยาลัยนะครับ Locant University นะครับแล้วก็ท่านที่2นะครับดร.กิโยมเนี่ยจากบริษัท Genalis ประเทศฝรั่งเศสนะครับซึ่งเป็นผู้พัฒนาเทคโนโลยีนี้นะครับโดยได้รับการ transfer patent จาก Professor Stefan นะครับเทคโนโลยีนี้นะครับโดยสรุปนะครับเป็นเทคโนโลยีใหม่ที่ใช้ในการแช่เยือกแข็งตัวผลิตภัณฑ์อาหารนะครับไม่ว่าจะเป็นเครื่องดื่มนะครับที่ในสไลด์ที่ดร.กิโยมได้แชร์ไปก็จะมีจำพวกกาแฟนะครับน้ำผลไม้สดนะครับจุดเด่นของกระบวนการนี้ก็คือว่าสามารถที่จะเก็บรักษาสภาวะของตัวผลิตภัณฑ์นะครับแล้วก็หลังจากคืนรูปเนี่ยยังมีความสามารถในการคงตัวของตัวผลิตภัณฑ์ตั้งแต่เริ่มต้นก่อนฟรีซได้นะครับโดยเฉพาะคุณสมบัติที่เป็นแก๊สโฮลดิ้งนะครับก็จะเห็นได้ว่ากาแฟก็ยังมีฟองอยู่นะครับผมแล้วก็อีกอย่างหนึ่งคือมีข้อดีตรงที่ว่าสามารถทำ phase separation นะครับหรือการแยกชั้นของตัววัตถุดิบนะครับซึ่งเป็นของผสมนะครับซึ่งพอคืนรูปแล้วก็ยังคงการแยกชั้นได้อยู่นะครับอาจจะเป็นลูกเล่นของผลิตภัณฑ์นวัตกรรมซึ่งอาจจะตอบโจทย์ความต้องการของผู้บริโภคได้ในอนาคตนะครับผมอีกอย่างหนึ่งก็คือว่าอีกแอปพลิเคชันที่มีความน่าสนใจก็คือการเก็บรักษาพวกเซลล์ของสิ่งมีชีวิตที่เป็น functional ingredient ในอาหารนะครับไม่ว่าจะเป็นพวกสาหร่ายนะครับที่มีสาร active compound ที่มีฤทธิ์ต้านอนุมูลอิสระนะครับหรือเซลล์ของจุลินทรีย์กลุ่ม probiotics นะครับซึ่งปัจจุบันเนี่ยมีความสนใจจากอุตสาหกรรมมากมายนะครับสำหรับการที่จะหาเทคโนโลยีในการเก็บรักษาคุณภาพของ probiotics ในผลิตภัณฑ์สุดท้ายนะครับผมสุดท้ายนะครับก็อย่างที่ทราบคือเทคโนโลยีนี้ยังไม่มีในประเทศไทยหรือในเอเชียนะครับแล้วทางโครงการเมืองนวัตกรรมอาหารส่วนขยายณมหาวิทยาลัยเกษตรศาสตร์ก็มีความสนใจที่จะถ่ายทอดเทคโนโลยีนี้มาใช้ในประเทศไทยนะครับโดยที่โฟกัสไปที่ Food SME นะครับอย่างที่เห็นไปนะครับที่บริษัท Genalis เนี่ยมีเครื่องมือในทุกระดับนะครับตั้งแต่ Lab Scale จนถึง Industrial Scale นะครับก็ขอให้ทุกท่านโปรดติดตามในตอนต่อไปนะครับว่าทางโครงการมีการนำเทคโนโลยีตรงนี้เนี่ยมาถ่ายทอดมาสาธิตแล้วก็มาประยุกต์ใช้กับผู้ประกอบการอาหารในประเทศไทยนะครับเพื่อให้สามารถผลิตภัณฑ์นวัตกรรมอาหารตามความต้องการของตลาดทั้งในประเทศและต่างประเทศได้นะครับก็วันนี้ผมขออนุญาตสรุปแล้วก็จบการบรรยายนะครับFood Talk นะครับ Special Talk นะครับในโครงการCross Border Technology Transfer นะครับเพียงเท่านี้นะครับก็ขั้นลำดับถัดไปนะครับก็ต่อให้คุณพงษ์พิภพนะครับได้กล่าวสรุปแล้วก็อำลาทุกคนไปนะครับก็สวัสดีครับผม
สวัสดีครับขอบพระคุณมากๆนะครับสำหรับผู้ช่วยศาสตราจารย์ดร.กิติพงษ์รัตนาพรนะครับแล้วก็โปรเฟสเซอร์ทั้งสองนะครับที่มาถ่ายทอดนะครับความรู้ด้านเกี่ยวกับ Cryogenic Nitrogen Technology นะครับอย่างที่อาจารย์ได้สรุปไปแล้วนะครับว่าถ้าในอนาคตนี้นะครับทางมหาวิทยาลัยเกษตรศาสตร์นะครับได้ประสานนะครับเทคโนโลยีนี้มาถ่ายทอดได้กับผู้ประกอบการได้เมื่อไหร่เนี่ยเราจะรีบแจ้งให้ทุกท่านทราบนะครับผ่านทาง Facebook Fanpage Live นะครับของInnopolis เกษตรศาสตร์ University นะครับและสำหรับผู้ชมท่านใดนะครับที่มีคำถามเพิ่มเติมนะครับถึงโปรเฟสเซอร์ทั้งสองท่านนะครับก็คือสามารถเขียนคำถามในคอมเมนต์ไว้ใต้ด้านล่างได้นะครับทางทีมงานจะรวบรวมนะครับแล้วก็จะส่งมอบให้กับทางวิทยากรเพื่อตอบคำถามผ่านคอมเมนต์ต่อไปครับสำหรับวันนี้นะครับกิจกรรมดีๆเช่นนี้นะครับจะเกิดขึ้นไม่ได้เลยนะครับถ้าเราไม่ได้รับการสนับสนุนจากเมืองนวัตกรรมอาหารส่วนขยายณมหาวิทยาลัยเกษตรศาสตร์และหน่วยบริหารและจัดการทุนด้านการเพิ่มความสามารถในการแข่งขันของประเทศหรือบพค.นะครับขอบคุณทุกคนมากๆนะครับและสำหรับลำดับถัดไปนะครับอย่าลืมนะครับท่านผู้ชมทุกท่านนะครับรบกวนช่วยตอบแบบสอบถามนะครับในแบบประเมินด้วยว่าในการกิจกรรมในครั้งหน้าหรือครั้งต่อไปนี้ครับท่านผู้ชมนะครับอยากได้กิจกรรมหรือว่าต้องการเห็นเทคโนโลยีใดๆใหม่ๆนะครับที่ทางเราจะมาถ่ายทอดให้ท่านได้รับชมนะครับก็สามารถเขียนมาในแบบสอบถามได้เลยนะครับแล้วก็ช่วยประเมินกิจกรรมในครั้งนี้ด้วยครับสำหรับวันนี้นะครับก็ต้องลาไปก่อนนะครับพบกันใหม่กิจกรรมดีๆในครั้งหน้านะครับผ่าน Facebook Live Fanpage ของ Innopolis เกษตรศาสตร์ University นะครับขอบคุณมากๆครับสวัสดีครับ
Recording stopped.